Okay, so for the practice test that I gave you yesterday, Nora requested the answers to it, so I'll give that to you. Okay. One is, this is for the practice test I gave you yesterday, the answers. I want to write this down. One is C. Two is A. Three is, everyone getting this? Want me to give you a minute? Okay, again, one is C, two is A, three is A, four is B, five is A, six is D, D is in dude. Seven is B.
Oh, that's okay. It automatically just switches to number 10. Also doesn't count.
There's no seven? Okay, I'll deal with, okay.
Just a real quick announcement for your class.
Sure.
Just from the office, folks, anybody thinking about withdrawing from summer school, there's a deadline and it's this Thursday, so I just want to make sure everybody knows that. This Thursday at noon, last chance to withdraw this Thursday. Okay? Any questions? No, we good?
Yeah, I think I had one fellow come to the office yesterday, so about that.
Yeah, if you do withdraw, you have to make sure you bring your textbook back, and we need parental approval, so either come with your parent or we need to talk to them on their phone. Okay? Awesome.
Thank you.
Thank you.
Okay, it just goes 1, 2, 3, 4, 5, and then the next page is just 10 to 15, and that's the end of the.
I knew that.
pieces, so.
I think it didn't print out for whatever reason. Okay, so number 10 is C. 11 is B. 12 is A. 13 is C. 14 is C. 15 is A.
Okay, so I have like 3 more questions on this actually. The other side is like pieces, so.
Okay, so let's continue on with the electric field. Let's go over a few problems with, whoa. Okay. Oops. Started down here. Sample 1. What is the magnitude? So what is the magnitude of the electric field strength. Sometimes you'll see the question worded, what's the electric field, or what's the electric field strength at a point where a 2 microcoulomb charge, actually, I should say test charge, experiences an electric force of 5.3 times 10 to the minus 2. So this is your force here. And this is the charge that's being acted on. So this is not the source, this is the small q. So what's electric field? Electric field, the magnitude is given by the electric force. It is a force. It's a force per unit charge. So you have to divide out the small q. So divide out the small q. How did I know this was the small q? It says the charge experiences a force. It's the one that's it's the charge that's experiencing the force that is the small q. It experiences the force. It's not the cause of the force. It experiences the force. That's what the small q means. It's what's experiencing the force. Okay? So how did I know to use this equation? Why didn't I use this? How come I didn't use this? I didn't use this second equation because there's no mention of, that's the source. There's no mention of the source. There's no mention of distance from the source. There's no mention of the distance. There's no mention of the source. There's only a mention of a charge that experiences a force, which is my clue that it's small q. And they also give you the force that it experiences. So Fe is the experienced force. By what? By small q. The force experienced by small q. Okay, this equation, by the way, always works in all conditions, in all problems. If in doubt, try to use this one. You won't always have enough information, but if you do have the information, it always works. This only works with a point charge. This is the equation for a point charge. What's a point charge? This source is a point charge. It's a proton. What's an example of a point charge? Point charge example is a proton, an atom, actually not an atom, but an ion. An ion is with some electrons removed. Electron. As opposed to what? As opposed to That's what a point charge is. What is a point charge not? Point charge is, this is not, if you see a picture like this, and it's got, let's say, negative charges on it, that's a plate. That is not a point charge. You can't use this, you cannot use that equation for it. Not a point charge. How do you know if it's a point charge? Well, it's any of these, or it just simply looks like this. If you see in a drawing like this, if it looks like, simply looks like that, that's a point charge. If they draw a circle with a charge, it's a point charge. And so the electric field is that. Where this is big Q, this is the source. Source of what? Source of electric field. Okay, let's go through another example. Example 2. What is the electric field? Strength. Midway. Between point charges. Of -3, 3.5 microcoulombs and +3 microcoulombs that are placed that are placed 4.4 times 10 to the -1 meters apart. Okay, here's a drawing. You can see automatically I just drew a circle, so that means this is applicable. If you can use it, use it. This is your equation you're going to use. That's one source. That's going to be my Q1. It's negative. Oops. Negative. Midway. Midway is 2.2. At this point, that's midway. This one's positive. Yeah, it's microcoulombs. Microcoulombs. So both of them can use this. I drew them as circles. That means they're point charges. So I can use that equation for both. I'm going to have an E1 due to a Q1. I'm going to have an E2 due to a Q2. Let's look at this point. Let's draw the vectors, because the question is, what's the electric field? It doesn't say anything about a magnitude, so I'm going to have to give direction as well. This is point P. What's the electric field at point P due to 1? The electric field, I'll just call it E1. The electric field due to source 1. How did I know it's to the left? Because if you placed a little small little positive test charge there at point P, it would feel attracted to charge 1. It would move to the left. Due to charge 1, due to source 1. You have to look at each source individually, one at a time. What about Q2? It's the opposite. The positive test charge, this is a small little positive test charge. It would be attracted to Q2, to the right. So am I going to draw this bigger or smaller? I'm going to draw this. I know just by looking at the size of the charges that E2 is going to be smaller. I won't always know that. So I drew it a little bit smaller. How do I know it's smaller? Well, the distance is the same. The only outlier is going to be the size of the source. The negative charge is bigger. So E1 is going to be bigger. That's why I drew it as a longer arrow. So let's draw these. That's E1. How am I going to connect them? Tip to tail. These are vectors, so you can represent them as arrows. How am I going to draw the resultant? From the tail of the first to the tip of the last. That is my net electric force at P, point P. Now what do I have to do? I have to just simply calculate E1 and E2. Calculate E1 and E2. And E net will be equal to E1 minus E2, whatever that is. And it's going to be to the left. So calculate E1 and E2. E1, same subscript. Subscript stays the same. I'm just going to put R, just R, not R1. It's the same distance for both, so R squared. And Q1 is 3.5. Don't worry about the negative. I know it's negative. The negative is already taken into account. When you drew this arrow, here, you drew it taking into account that Q1 was negative. So don't worry about that. Direction is taken into account. When we're dealing with vectors, the direction is taken into account by drawing the correct diagram and then writing the overall direction of the net electric field at the end, in this case to the left. So you could put negative if you want, but it's already taken into account in the diagram. Don't forget to square it. This becomes very important. Later on, we're going to come up with an expression where there is R, not R squared in the denominator. So be very careful. When calculating the field, you need to square the denominator. Same thing as force. Okay, so this works out to be 6. I'll carry an extra digit, 6.51. Is that right? Did I include the right unit? It's close. It is a force, but it's a force per unit charge. You have to divide it by coulombs. It's how much force is acting on a single unit of charge. That's what electric field is at that point. Okay, I'm just calculating magnitude. Direction is taken into account here and in the final answer. When you're calculating the net electric field, the rule is just calculate the magnitudes. Find the direction by drawing a diagram. You do need a diagram because it is a vector. It is not a scalar. If it's a scalar, no diagram needed. If it's a vector, you need a diagram with arrows and a big fat arrow at the end to show the net electric field direction. Okay, E2. Same subscript. 2 here, 2 here. R squared. Yes, it's R2, but it's the same distance for both, so I don't have to distinguish it. So Q2 is 3. Micro, that little u means 10 to the minus 6, 1 millionth. Distance is the same. It's halfway, so it's half of what was given. It's 2.2 instead of 4.4. Now it works out to be, that's not right. That's not right. 5.58. Did I make a mistake? It's saying, oh, I did make a mistake. E2, what's the direction of E2? It's to the left. It's not to the right. My mistake, sorry. Let's change this. It's okay. If you go back to this charge here, which direction would it experience a force? It would be pushed away from Q2. Experience a force this way. So E2 is this way. That changes my diagram here. Sorry about that. My E2 is here. My net force is then, my net electric field looks like this. Still to the left, but I'm going to add these two. Add them. I'm going to add these two values. E1 plus E2. Okay, that works out to be 1.2 times 10 to the 6. It's still to the left. They both point to the left. Yeah.
What if it was a negative charge?
Oh, good question. Yeah. So you mean going back to this?
Yeah.
Everyone got that? We'll go back and change it to a negative. Then it's what I said originally. Yeah, I made the mistake.
But like, why do we use a positive charge? Because we always do. But like,
It's an arbitrary definition that physicists made up. So they could have chosen a negative test charge. They chose a positive.
is there a way to convert it to negative? Like,
No, stick with what you're given. Yeah. There's no point. You got to stick with what the definition is. That's what physicists use. So your question was, what did I do here? I wanted to lasso it. What the frick? Your question is change it to a negative, right? Change this to a negative.
Yeah.
Then it's what I would say.
Oh,
I
sorry.
said earlier.
I'm
No, yeah, you can't change the test charge.
Like, what did you do?
Why would you? You stick with what you're given. That's the definition in physics. I told you from the beginning. A definition is a man-made construct. It's man-made. Sometimes they have reasons. Sometimes they just start with a random decision and they stick with it consistently. So you've got a man-made concept. So just stick with what they decided it to be so that you can communicate clearly. If you change this to a negative, then it's what I said earlier. Okay, I don't. Where is it? I think I erased the original diagram. Yeah, the original diagram got erased. I think I cut it out. Great. Oh well. No, it's not giving me anything. Not going backwards. Frustration. I'm moving it back. This originally was positive. If you change it to a negative here, so this is Q2, this is Q1, then you'd get what I said earlier. Put a little positive test charge here. Test charge, due to this second charge, would feel pulled in this direction. In that case, your E2 would be to the right. E1 would still be to the left. In that case, net electric field would be what I wrote earlier, E1 minus E2. Definition, man-made. Okay, so some charges and masses that you need. You're going to use these. I would put this on your formula sheet. On a test, I'd probably give it to you, but just in case, put this on the formula sheet. You need the mass and the charge on an alpha particle. You already have it for the electron and proton. I'll give it to you for the alpha particle. Put it on your formula sheet, please. That's the mass and charge of an alpha particle. What's an alpha particle? Alpha particle is a helium ion. It's a helium. It's a helium atom with the electrons stripped away. Okay. So you can chart, let's see, try the following. Why did they give you that? On page 279, You can try numbers 1. Try 1 to 3. And then on page 280, number 5. Five to 7. Look on that.
Here we have.
What the heck? Okay, I loaded the videos from yesterday. There's one on some of the gravitation problems we went over. You might want to look at that later. Time is it? 26. Yeah. It's 1 million. 10 to the minus 6. Yeah. Five to 7. I'll be right back. Then we'll go over it. Where are you at? 1 to 3 you got done? Alexa, what you got done? Up to 5? Okay. I'll be back. Felix Schwartzman. Yeah.
Newtons per kilogram? I think Newtons per kilogram. I'm just gonna email them on everyone to have. When is that? August 7th?
August 7th.
7th?
6 is the last day.
Oh, yeah. Oh, yeah, I'm sorry to call it here, but most likely Saturday, August 7th. Yeah, well, it says, but it's like,
Close is for the point card, or the, yeah, filter, and then meters three.
Oh, so then that's why.
Like, is it not-
I don't know.
Yeah. And this is just meters per. Is this right? The gravitational observations for.
no thing, they just show up and have it on this for their life. And then they just send it for help. That's something that I'm hired to do on this. I think you'll have to do.
So many different uses for meters. So the gravitational. Because it's electronic takeout over here, this is meters. This is mass. Yeah, this is an odometer, right?
Me, Andy,
The gravitational constant is times meters squared per kilogram.
it's not first.
It's not meters, it's right here.
So we.
It says meters times meters squared per kilogram, so meters squared times some distance squared. X goes down. Yeah, so that's it. What? Oh, wait, no. No, it's 2 kilograms, right? You mentioned something, no, I can't believe it. Yes. This is a news hour because.
I didn't know.
This is mass and mass, so gravitational constant is divided by two.
What?
We're gonna get yeah.
Yeah.
Sheet for gravitational potential energy.
So like.
Gravitational potential energy. Did I give you a sheet for it? Yes, here you go. This is what I think you're referring to. Okay.
Apparently you're not supposed to like send kids there, so like you know it's visible, but like it's just like about like it's not as visible. But then like you just die of old age like 2 years later.
What are you talking about?
Oh, old. There's like M. Night Shyamalan has like this new film, Old.
Oh, yeah. Is it good?
I don't know. But like
He was so good when he first came out. Then it's kind of like hit and miss after that.
and this was about like this family who goes to a beach and then like the beach makes them age rapidly, so they
Oh, yeah, that one. That actually looks kind of neat
like
in a sick way.
and like the children rapidly age.
Okay. I'm not able to get onto the network. Can't join. Check your internet connection. Why?
Let me see. They should have some.
Hmm? My internet connection is down. Interconnect connection, why? Okay, I will use my phone for you then. It will burn up a little energy. What am I gonna do? Hotspot. The connection isn't safe, okay? Ah, no, done. Uh, okay, let's go over page 279. Number 1. So what is what's the magnitude of the field? Okay, so they give you the charge. That's your clue to use this equation. They give you the charge and they give you the distance. That's how you know. And it says also point charge. This is the equation for a point charge. This is the electric field equation for a point charge. It will give you electric field strength. Okay, so what's the K? 9 times 10 to the 9. That's in your formula sheet at the back of it, in your table of constants. 8 microcoulombs. 8 times 10 to the minus 6. The distance is 7.5. Don't forget to square it. That works out to be 1.3. Newtons per coulomb. Number 2, field strength. This is the field strength. Same thing as acceleration due to gravity. It's given by the force of gravity divided by the mass. We're just going to calculate the absolute value. It's very similar to this, the electric field. What is the general equation for the electric field? That works in all cases, whether it's a point charge or not. Electric field is the force divided by charge. Gravitational electric field is the electric force divided by the charge, point by the test charge. The gravitational field is the gravitational force divided by the test mass. Mass that's being acted on. Calculate the field on Mars. Okay, so what is FG? For a planet, that's your FG. For any object, that's your FG. What cancels out? The test mass. You don't need the small mass. That's it. We just need the mass of the planet and the distance to the point in question. I'm going to write it down below here. It's a weaker constant. It's not 10 to the 9, it's 10 to the negative 11. Mass of Mars. The distance, again, don't forget, in this case, it's to the surface, so you're going to use the radius of the planet. About 3.5 million meters. Don't forget to square it. And that works out to be, it's not 9.8 because it's not the Earth. Newtons, similar to electric field, it's not newtons, it's newtons per whatever you're dividing it by, in this case, mass, kilograms. It is not 9, obviously it's not 9.8 because 9.8 is the Earth. That's what it would be at the surface of the Earth. It's almost 1/3 that of the Earth. It's a smaller planet. Could we live on Mars? Given this is, yeah, we could, but we'd suffer because of the smaller or lesser field strength, less of a pull per kilogram. So we would lose muscle. That could have other effects as well. So they would have to create, I suspect they'd have to create some sort of artificial gravity for you to live on there. To add to that, to get it up to this. No, I think they'll figure it out. You know what? I already think that I think we already have, they're already doing experiments. There was an experiment in, I think, the Ukraine in the late 90s. He took mercury vapor and he accelerated it really fast, like supersonic speeds. And now people couldn't repeat it because I don't think they did it properly, but they were able to lessen the gravity. So they should be able to reverse it as well, I think, eventually. They're able to lessen the gravitational field strength above the plate, above the spinning gas. Other people are doing experiments on it, but it's all top secret black ops stuff. NASA tried to repeat it, but they didn't even do it properly. And then they said it didn't work. But you can't, that's the problem with these experiments. If you see a breakthrough, most of the time, the critics are right. But if you look at the experiments that are performed by the critics, make sure they're done properly. In this case, they didn't do it properly. So it's still a question as to whether, I think there's something to it. Because other people repeated it, and we're getting similar effects in private laboratories. But it's not been repeated, so we don't really know yet. Interesting fact. Okay. Don't laugh. Anti-gravity will exist. They'll be able to control gravity. Maybe in your day. Maybe when you're older. Then you'll look back and you'll say to yourself, oh my gosh, he was right. I made fun of him. I laughed at his ideas of gravity being controlled, and he was right. Yeah, it's okay. You can laugh at me now. I don't care. He won't be in the future. Okay, let's go on here. Electric field strength. What do we have? At a point, we have the charge. Check. we have the field strength. That's kind of odd. Normally we calculate it. We have the field strength. The question is, what is R? That's the question. So just rearrange, cross multiply R times E. Okay, and divide by E. Then take the square root. K is 9 times 10 to the 9. Q, in this case, is 4.6 microcoulombs. Electric field, 2.75. Okay, and that works out to be 3.9. Meters. The R is measured in meters, just like gravity. 4, we didn't have to do 4, right? I think I said to do 5. Okay, read over 5 carefully to yourself. Remember, before you begin, the charge on an alpha, that's a symbol. That fish means alpha. It is the Greek's first letter in the Greek alphabet, alpha. Okay? So the charge on an alpha ion, alpha particle is just a helium ion. Helium has 2 protons. Each proton has a charge of 1.6, so the charge on an alpha is 3.2. Okay? So what's the electric force that a proton would experience? A proton is half of the alpha, just 1 proton, 1.6. Okay, so let's look at the force acting on a proton. What is it? That's right, the force acting on a proton. What is it equal to? K Q. One sec here. Q proton. That's the force on a proton. This is the source that's acting on the proton or the alpha particle. It's the same source, doesn't change. Okay, for the alpha particle, it's the same source, except now we're going to switch it from a P to an alpha. Why is it a different force? Why did I put force alpha? Because it's a different charge that's acted on. It's an alpha. Okay, what do we want? We want to divide the proton force by the alpha force. Do the same thing on the right. So what's going to cancel out? Q is common to both. K is common to both. R common to both. All of those cancel out. What are you left with? Fp over F alpha is equal to charge of the proton over the charge of the alpha. What's the proton? The force on the proton is just the force on the alpha particle times the ratio of the charges. That's all. Okay, so what's the force on this? Force on the alpha is 0.25. What's this? This is 1.6. What's this? This is 3.2. Yes, I know they have exponents, but they're the same, right? I'll write them in for you, but you don't need that. They're the same exponent. That's why I originally didn't write them. They just cancel out. What is this? 1.6 over 3.2 is just a half. It reduces to 1/2. So this is just 0.125 newtons. That's number 6, pretty easy. It's just force divided by charge. I'll just give you the answer. Is that right? Did I give you the right unit? No, newtons per coulomb, yeah. Seven. Okay, this is a 2-part. Read it over again just so you're clear on what I'm doing. Okay. I want the acceleration. What's it given by? First thing that should come to mind when the question is what's the acceleration is net force is equal to ma. So divide the mass into the net force, you got the acceleration. Do I have this? I can find the net force. It's just equal to whatever the electric force is. That's the only force acting on it. So that is the net force. So if I can solve for this, I've got my net force. And I can solve for the acceleration. Do I have the electric field? Yes, that's given. Do I have the charge? Yes, that's given. So I can solve for the force. So I get, that's my force. And yes, it's a net force in this case. How do I know it's a net force? It's the only force acting on it. It must be the net force. Alpha particle. What's the charge? This is an alpha. I just told you need that table. I gave it to you up above here. That's why I gave it to you. It's 3.2. Whoa. You have it. You can memorize it if you want. It's twice the charge on a proton because it's made up of 2 protons. So it's 3.2 times the electric field, which is given, 7.6. That looks like a 4, right? Okay, and that works out to be 2.4. I'll carry an extra digit. Newtons, that's your force. That's this. Just divide it by the mass. Mass of what? It's the alpha. Mass of the alpha. Do you have it? Yes, I gave it to you. Go back to here. It's in this table. 6.65. Okay, so A is net force divided by mass of the alpha. 6.65 times 10 to the negative 27. So this is going to be pretty small, big, actually big. Big, because this exponent is a lot smaller than this. Is that the right unit? What's the unit for acceleration? Okay. Okay. We got one more topic to cover. Then I'll give you some homework. You can work on the homework after that, or you can study for the test tomorrow. It's up to you. But we do have to move ahead just on one more topic. It's the organic. This guy does a good job. Electric potential. What? You like this guy?
With regard to the charge.
You do. Okay. Last topic for today. Electric potential. It is a scalar. This is not a vector. Do not get it mixed up with electric field. It looks the same or similar. Looks similar, but it's not the same. It is a scalar, which means you don't have to draw arrows when you add them. Okay, ready?
Electric potential is defined as potential energy divided by charge. In some physics textbooks, you'll see.
Okay, this guy's making 110,000 a month.
A capital U represented as potential energy. Now, there are different types of potential energy that you need to be familiar with. There is elastic.
Okay, the symbol for potential energy is usually, the notation is PE. Sometimes you'll see the symbol U. Those are interchangeable.
Potential energy, that is the energy stored in springs. There's gravitational potential energy, which occurs anytime an object is above ground, which it has the ability to fall. And then there's electric potential energy, which is what we're going to talk about. So if I use PE or U in this particular video, I'm using it with reference to electric potential energy. So V is electric potential. PE, electric potential energy. Make sure you notice the difference between them. They sound similar, but they're different. Electric potential is measured in volts. 1 volt is equal to 1 joule of potential energy per 1 coulomb of charge.
Okay, so it can get a little confusing. Lots of definitions in this section. This potential energy, as he said, is electric potential energy. Basically, the amount of energy a charge has as a result of its position with respect to another charge. Okay? Electric potential, another definition, electric potential is defined as the potential energy divided by the test charge, small q. Yes?
For 1 joule over 1 charge.
1 joule over 1 coulomb is the unit for electric potential. And for joule per coulomb, we summarize that. Instead of joules per coulomb, we usually use the word volt. It's the same thing. Volt is the same thing as joule per coulomb. It's just obviously quicker to say volt. So it's related to what you call electricity. Electric potential is related to the voltage of a battery.
So an electric potential of 5 volts means that a 1 coulomb charge has 5 joules of potential energy. An electric potential of 12 volts means that a 1 coulomb charge has 12 joules of potential energy with respect to some reference point, of course. Or you could say that 2 coulombs of charge has 24 joules of potential energy. So electric potential is simply the ratio of electric potential energy per unit charge. So now that we've defined electric potential as potential energy per unit charge, let's relate it to something more familiar. That is a voltage. A voltage is electric potential difference. Voltage is the change in electric potential.
Okay, so voltage is what you refer to as the voltage of a battery. That is related to electric potential. How? You take the difference in two electric potentials and you'll get the voltage found in the battery. So on a battery, you've got two terminals. You got a bottom and a top if you're talking about a triple or a double A, right? There's a positive and a negative terminal. Each terminal has its own electric potential. The difference between them is the voltage of that battery. So with the double A, what is it? 1.5. With a car battery, there's two terminals. The difference, each of them have an electric potential. If you took the difference between those electric potentials between the terminals, you get the voltage. In that case, for a car battery, it's 12 volts.
By the way, you may want to take down these notes if you have a piece of paper and a pen with you, or a sheet of paper.
That's another definition. Voltage is the potential difference, electric potential difference. I can't keep answering because I'm going to go through this. I'll let you know.
So voltage would be the difference between the potential at B and the potential at A. So you can write it this way. So if you were to see VBA, that means VB minus VA. If you were to see V.
Okay, this is the symbol for voltage. What is voltage? It's just a potential difference. This is a potential at B. This is a potential at A. The difference between them would be what we call voltage of a battery. So you might have one terminal that's, let's say, 24, and another terminal is 12 volts. The difference between them is 12. That's the voltage of the battery. This is just another, VBA is just another notation or way of writing potential difference or voltage.
AB, that means the difference in potential at A minus the potential at B. So let's say we have a resistor. A resistor is an electronic component that is used to basically control the flow of electric current in a metal or in a circuit. Now let's say we have 2 points of interest across this resistor. We'll call this point A and point B. Actually, let's make this B. Sometimes my computer acts up. Let's do it that way. Let's say B is at 80 volts, A is at 20 volts. The change in V is 80 minus 20, that's 60. The 80 volts represents the electric potential at B. 20 volts is the electric potential at A. So this is VB and this is VA. This is the voltage. Voltage is electric potential difference. It is the difference in the electric potential between 2 points. So hopefully this helps you to see the connection between voltage and electric potential. The electric potential at B is 80 volts. The electric potential at A is 20 volts. But the voltage across the resistor is 60 volts. So we could say VBA, which is the electric potential at B, minus A, 80 minus 20, that's 60. Or we could say VAB, 20 minus 80, that's going to be negative 60. So let's use another example to help you see the difference between voltage and electric potential. So let's call this B, and let's call this A. So let's say for B, this is at 90 volts, and A, it's at.
Want to know the best way to potentially make a big income online? By making lots of small incomes online.
Yeah, sure.
at negative 30 volts.
Yeah, okay.
The electric potential at A is negative 30 volts. The electric potential at B is 90 volts. So what is the voltage across the resistor? Go ahead and calculate VBA and VAB. So to calculate VBA, it's going to be the final value, VB, minus the initial value, A. So we're going from, when you think this, we're going from A to B, initial to final. So that's 90 minus negative 30. So that's positive 120. So VBA is positive 120. Now, if we want to calculate VAB, in analyzing the direction, we're going from B to A. So B becomes the initial value, A becomes the final value. So it's final, VA minus initial. So A, VA is negative 30, minus VB, which is positive 90. So we get negative 120. So let's think about what's happening here in terms of the direction in which we're moving. So during the first part, we're going from A to B. Is the potential increasing or decreasing? As we go from A to B, it changed from negative 30 to 90. So the potential is increasing. Therefore, we got a positive value. Now for the second part, we went from B to A, from a high potential to a low potential. So the potential is decreasing, thus we can see why the change is negative. So I wanted to help you to understand the reasoning behind these two formulas, so that if you understand what they mean, you'll remember how to write them correctly. Now let's talk about how we can calculate the work done when a charge moves to a certain voltage. Let's say that the direction of motion is from point A to point B. So the voltage, which in this case is going to be VBA, that is the potential at B minus the potential at A. And if you recall, electric potential is equal to the electric potential energy divided by the charge. So VB is going to be the potential energy at B divided by the charge. VA is going to be the potential energy at A divided by the charge. Now I'm going to factor out 1 over Q. Doing so, I will get the potential energy of B minus the potential energy at A. Or we could say the change in potential energy. So we have 1 over Q times the change in potential energy going from A to B. Now some other formulas that you need to be familiar with are these. Work is equal to the positive change of kinetic energy, but the negative change of potential energy. In a system where energy is conserved, as kinetic energy increases, the potential energy decreases. Think of a ball that's fallen down. As it falls from a certain height, its potential energy decreases, but it's speeding up as it approaches the ground, so the kinetic energy goes up. This is true when the only forces acting on the system are conservative forces. That's when mechanical energy will be conserved. If there are non-conservative forces acting on the object, then this may not apply. So just something to keep in mind. But what we need to say from this is that work is equal to the negative change of potential energy. So therefore, the change in potential energy is equal to negative W. So we have 1 over Q times negative W, which we can write as negative W of Q. And that equals delta V. So delta V is equal to negative W over Q. We can multiply both sides by negative Q to get an expression for W. So the work done by a charge or on a charge as it moves through a certain voltage is this equation. It's negative Q delta V. Now let's work on this equation.
Yeah, you need to know that last equation here. Oops. 1 second. That's what I wanted. Why didn't he do it? Anyways, flip back to this. Just make sure you got that last line down.
energy. Now, we also know that 50, now, forces act, the potential,
Come on.
Wow, you have braces, everything's hands-free.
if there are non-conservative forces acting on the object. I forgot to the word charge. Number 2, charge. It's 300.
Need that last equation. Come on.
Required. So now let's work. We're on a charge as it moves through a certain voltage. Is this equation?
Need that last equation. Okay. We'll come back to that. Make sure you have that down.
Let's talk about electric potential, V. This is confusing. This is
Okay, so this is focusing on, we'll come back to what we just wrote down on how work is related to electric potential, but this next video refers to the potential at a point in space due to a point charge. We're going to start with that, how to calculate that.
one of, if not the most confusing ideas in all of physics. For one, it sounds just like electric potential energy, but it's not. This is different. It's related to electric potential energy, but the electric potential V is different from electric potential energy. That was a poor choice in naming. And the other reason it's confusing is that the electric potential V is a number. Just a number, that's it, associated
It's a
with
scalar.
in space.
Make sure you have that
It's
down.
abstract.
Electric potential is a
Abstract
scalar.
idea. You can't
It's not a
go
vector.
hold electric potential in your hand. It's a number, an abstract number at every point in space. Here's points in space. We just put circles around empty spots on the screen. There's like nothing here. Just put circles here. These are circles around empty points in space, just so we can talk about them explicitly. And, well, if there was no charge around, if you literally had an empty universe, the V value at every point in this universe would be 0. It'd be 0 there, it'd be 0.
Let me just
Here's
check
the
on
number.
something. Sorry, 1 sec. Sorry about this.
Divide by the distance. So I divide by a distance, I divide by the R value. And
Good.
the R value
That's
is
good.
9. Electric potential value is not 0. We just stick a charge in here. Just stick a big old positive Q at some point in space over here. Stick a big old charge. We'll stick it right there. Now, points in space around this charge will have a V value that's non-zero. And it'll be big if you're near this Q. The V values around here are going to be really big. And then the V values way out here will be smaller. The farther away you go, the smaller it gets. And why do we care? Who cares? The reason we care is this. The units of electric potential are joules per coulomb. So electric potential has units of joules per coulomb. That gives you a hint of why you should care. We care about joules. Joules are energy. So if something can have energy, that's useful. You can get work out of that, or it can turn into kinetic energy. And joules per coulomb, that lets you know, all right, well, if this point over here happened to have, say, 100 joules per coulomb, let's say the V value at this point in space happened to be 100 joules per coulomb, what that means is, remember, there's nothing there. But if there was something there, if we happen to take, maybe we had a positive 2 coulomb charge, We took that charge and we put it there at that empty point in space. Before we put it there, the V value was 100. When we stick it here, who cared? Why do we care about this 100 value? Because look at it, it's 100 joules per coulomb. That's what V, the electric potential, is telling us. So if it's 100 joules per coulomb and I stick 2 coulombs there, how many joules of energy do you think it's going to have? It'll have 200. And that's the key. That's why we care about electric potential, because it lets us find electric potential energy. Either PE, sometimes people write electric potential energy as U. So the formula is just Q. You take the Q that you stick at that point in space, in this case it was 2 coulombs. Take whatever Q there is, multiply it by the value of the electric potential, and that tells you how many joules there will be for the charges in that region. So this electric potential energy is between these 2 charges here, the charge that created the V and the charge that you stick at that point. And the V is a quick way to figure out how much potential energy, electric potential energy there would be. So in other words, in this case, since I had 2 coulombs there, I take my 2 coulombs and I multiply by 100 joules per coulomb, because that's the V value, and I get that there are 200 joules of potential energy now stored between these charges. So that's why we care about electric potential V. It's a way to figure out the electric potential energy for a charge that's placed at that point in space that has that V value. But how do you get this V value? If I hadn't given you the 100 joules per coulomb, we wouldn't have been able to figure this out. We need a way to figure out the V
Okay,
value.
so why do we care about potential energy? This is a positive charge, that's a positive charge. The amount of potential energy has the ability to make this 2 coulomb charge move. The greater that potential, the faster it'll end up moving. So it's related to its eventual speed.
You at points in space based on the charges creating them. Because charges create the V value. There's a formula for it. And the formula says that the V, the electric potential created by a point charge, is equal to K. K is the electric constant, 9 times 10 to the 9th, and it has units of Newton meter squared per coulomb squared. That's always K. Take that K and you multiply by the charge that's creating the V value. So in this case, it's this Q. This positive Q here, whatever Q it is, creating the V value that you want to find. And that's key. If you plug in 5 coulombs here, you're finding the V created by that 5 coulombs. If you plug in -3 coulombs, you're finding the V created by the -3 coulombs. Sometimes there's problems with multiple charges in it, like this one. And this Q has got to be the charge creating this V. Not the charge you placed at that point in space. Don't put the 2 coulombs up here. Put the charge creating the V value that I want to find. And then you divide by the distance. So I divide by the distance between this charge and the point in space that I want to figure out the V value at. Some people call this the radius. I don't like calling it the radius. It makes it sound like there has to be a circle. There doesn't really have to be a circle. This R would be the distance from this point of charge creating this V value to the point in space where I want to determine the V value. That's R. So this is R. So how would we determine this? Well, let me just give you some numbers. Let's say the charge we stuck here was 1 nanocoulomb. Nano is 10 to the -9th. So let's say that was 1 nanocoulomb. And let's say the distance from this charge to this point in space was, let's say it was 9 centimeters. And I want to know, what's the V value? Well, I can solve for it now. We've got our formula. The V would equal...
Make sure you have that formula down. That is the electric potential for a point charge, something like a proton or an electron. That's the equation for it. KQ over R. It's not KQ over R squared, not the electric field. It's KQ over R, and it's a scalar. It's just a positive or a negative value. It has no direction. Yep. You get it. You get it from, if you go back to what was said in the previous video, it's defined, it's a definition. It's defined as the potential energy per unit charge. You get it from that. What is this? Again, you're going to have to We didn't derive it because we don't have the calculus, but the potential energy is just KQQ over R positive. It's similar to the gravitational potential energy, and it's derived the same way. It is a negative if they're opposite charges, but we won't get into that. When you derive it, you'll just get this value divided by the small q. Small q cancels out. That gives you K, pardon me, this stupid story of my life with these things. I'll get it later. The small q cancels out, and you get K big Q over R. That's how you get it. When is it applicable? It's applicable for a point charge. When you use KQQ over R, that is the potential energy of a point charge. That's how they get it. Should be on your formula
A
sheet.
is 9 always times 10 to the 9th, and it's newtons meters squared per coulomb squared, and then I multiply by my charge. I told you that the charge here was 10 to the negative 9th coulombs, 9, and my distance I divide by the R value, and the R value is 9 centimeters, but be careful, everything's got to be in terms of meters, kilograms, and seconds. When you're doing physics with constants, look at this is in terms of meters. I've got to use meters here. So 9 centimeters is 0.09 meters. And if I multiply all this out, what you'll get is 10 to the negative 9th cancels this 10 to the 9th. My powers of 10, these just go away. And then I have 9 divided by 0.09. That's going to equal 100. So I chose this so that we got the same answer down there. Get 100 joules per coulomb. You might be like, where did the joules come from? And how does this joules per coulomb? Well, let's look at it. If we took, look at one of these meters cancels one of these meters, or one of these coulombs cancels one of those coulombs. What are we left with? We're left with Newton times meter over coulomb. But Newton times meter, that's force times distance, that's joules. That's where we get joules per coulomb. So this really does give us the number of joules there will be at a point in space per coulomb of charge that you put there. And it works for any point. You pick any point. If I picked a point twice as close, it's half as far away, say some point over here. Let's say this R value here was only 4.5 centimeters. Well, I'm dividing this by R. So if the R is half as big, this point over here would have a V value of 200 joules per coulomb. And the closer I get, if I went even closer, if I went to a point that was 3 centimeters away, well, this is a third as much as this other distance. So if I'm only dividing by a third as much distance, I should get 3 times the result. This R is not squared, it's just R. So this point would have a V value of 300 joules per coulomb. This tells me if I wanted to get a charge to have a whole bunch of potential energy, I should put that thing nearby. I should stick it over here. This would give me a lot of potential energy. Not quite as much. Even less. The farther I put my charge, the less potential energy you would have. There will be no potential energy until there is a charge. There will just be electric potential. But once you place another charge in that region, you go with the first one, then you'll have electric potential energy, and this would be a way to find it. Q times the V that you get out of this calculation. You've got to be careful though. Sometimes people get sloppy.
Okay, so small q is what's being acted on. Big Q, which you use to calculate the electric potential, is the source. Why it's important. That's why I originally wrote in my equations big Q, small q. Big Q is the source. It's what, in this case, creates the electric potential. Okay? This formula is very similar to electric field, except there's no R squared, just an R. And it is a scalar. It's only positive or negative. Okay, so try on page 286. Try numbers 1 and 2. That's it. So on page 286, one and two. Do that. You can do that or you can study. That's your homework. Not much homework tonight because you got to study for a test. Yes?
For a long time, volts, is it like where it is going to be really out there? It's like it's where is volts placed in that diagram that's on the
In the video diagram?
video? Yeah. Like is it placed where, right on the bottom right?
Where is the voltage on what?
Like where does
A voltage is calculated for a particular point in space away from the source charge. So you could choose any point you want. He chose this point here, which was a distance of 9 centimeters, which means you insert 9 into your R, convert it to meters. He was just basically saying the closer you get, because they're both positives, the closer you get, the more repulsion basically there is, and therefore the more potential energy, and therefore the greater the electric potential. What does electric potential give you the capacity to do? Well, in this case, the potential, like I said, is greater the closer and closer you get to the source. It has the potential to release, once this point charge, this small q is released, the greater the potential, the greater it has to make that speed up. The faster it'll go, the greater the potential. Right? It's kind of like, what has got greater potential? The brick at this point or a brick that's another 2 meters above? Obviously a brick that's farther above. Potential to do what? Move faster before it hits the ground. It's got a farther space to, in this case, it's got a greater distance to accelerate down through. Therefore, it's got more potential. Potential is related to the final speed. The more potential, the more final speed or greater the final speed it'll have. 300 is closer, so if you were to release this small q from this point here, it would be moving at a faster speed when it reached the same point over here, let's say. Let's say you're comparing this point, it's going to move from here to here. If you released it from here, it would be at a faster speed when it reached the final position than it would if you released it from this point here. Because at this point here, the potential is greater. If that helps. Yeah.
I have a question about the review.
Sure, which one? Yeah.
Okay, it's 24. The one with Tarzan.
Sure. I'm going to give you a list. Some people have asked in the second review sheet, could I narrow it down? Is this the first one? Nora, this is the first one, right? First one or second one? Yeah, some people wanted to know, would I narrow down some of the questions in the first handout on circular motion, the one that you did the problems for the assignment on? Yeah, I've got a list here. I got a photocopy of that, so.
And
Whoa.
How much is College Happy making every year?
Same. That just on physics, and chemistry, about the same as him. And math, right? Maybe more.